All right, so the last thing we're going to look at this week is the second half of section 6.5, where we actually get into solving a triangle. And basically all that solving a triangle means is to figure out the lengths of all the sides and the measure of all the angles. Now, in order to solve a triangle, I have to give you some information to start with. And there's really two different situations that you could have. Right? You need to have 3 pieces of information in order to solve a triangle. There's 6 things you have to solve for. But there's one thing that's going to be common to every triangle that you're not going to have to worry about. They're all going to have a 90. So there's one piece of information right there. But I said I need to give you 3. So that's 1. I need to give you 2 more things. I can either give you one of the other angles and a side, or I could just give you 2 sides. Depending on which situation you have is going to control how you solve it. One of the methods, you're not solving for any, you don't have to do anything too fancy to find an angle because you're going to be given the 90, you're going to be given another angle, so you're going to know 2 out of 3 angles right off the bat. So that's going to simplify finding the angles. All right. In the other method, you're not going to know the angles. You're going to be given a 90, but you're going to be given a couple sides, so you're not going to have anything to subtract from 180 in that case. We'll talk about what you have to do. So keep in mind, we can use the Pythagorean Theorem to solve triangles. That will work. And all the angles in a triangle have to add up to 180. One general rule about the whole process, I generally do not want to use something that I've calculated to find the value of something else. Why do you think I want to avoid using something that I found to find something else? I would rather use the things that are given to me. Yep?
You make a mistake.
Okay.
Like if you make a mistake finding one of the sides, then that could throw off your angles.
Yep. All right. If you make a mistake on one thing and you use that to find something else, well, guess what? Now that's wrong too. Whenever we're solving these kinds of problems, you're always going to use the information that was given. Don't ever use something you found to find something else. Okay? Go always back to what was given to you. So there's only 3 trig functions that we need to do this. Sine, cosine, and tangent. The other 3, the secant, the cosecant, and the cotangent, we don't have buttons for those on the calculator. So it's easier to use the ones we have buttons for. And with these 3, it covers everything. Okay, you need a trig function that would cover involving every combination of 3 sides that you could have. And these cover. It covers the opposite with the hypotenuse, the adjacent with the hypotenuse, and the opposite with the adjacent. There's no other pair you have to worry about. That covers them all. And the way you figure out which trig function to use is you draw a diagram, you look at the side that they give you, and then look at the side that you want to know. So you'll know one side in the first case that we're going to do. You'll know one side, you're going to want to find one side, and look at what the names of those 2 sides are. And by names, I mean give them the opposite, adjacent, and hypotenuse labels. And then pick the appropriate trig function that involves the 2 sides in your problem. So, let's look at this one. It says we have a right triangle with a 37-degree angle, and the hypotenuse is 8. So what did I say the first thing you want to do is, so you can easily visualize what's opposite, what's adjacent, and what the hypotenuse is? Yep, we're going to draw it. Okay, that's the very first thing we'll do. It doesn't matter how you draw your right triangle. You can face it any way you want. But we do have to label what we know. Let's put the 37-degree angle right there, and the 8 right there. Now, mentally, it's easier if you give names to everything else. So that way you can keep track of, instead of just saying, oh, the left side, well, let's name the left side with a variable. So, I mean, you can name all the sides if you want. A, B, C. And what angle is always across from A? Anyone remember the Greek letter for that? Yeah.
Alpha.
So that angle is always alpha. And the Greek letter across from B? Theta. So sometimes, well, most of the time, what I do is make a table to organize that information. You don't have to give a name to the third angle because it is always going to be 90. When we do this again in the future, we're going to do it when it's not 90, and we'll give it a name. But for now, we'll just call it the right angle. And we know alpha is 37. And we know C is 8. All right, so I need to find A, B, and beta. What can I find there pretty quickly without too much work? Really, you probably could have found this before I taught you anything about this week. Madison?
Beta.
Beta, and how would you get beta?
You would just subtract 37 and 90 from 180.
Yeah, or just subtract 37 from 90. Because that your 37 and beta have to add up to 90, or you won't get 180. So, yeah, we'll just do 90 minus 37, and that tells me beta is 53 degrees. Generally, when we are solving a right triangle, I think these problems will be in degrees. Okay, so we've got beta. Now we need to find A and B. When you're trying to solve for one of the sides, in this case, you have to use 3 pieces of information. You want to use the given, and now pick a side that you want to find. We can do A or B. So Caleb, which one do you want to do first?
A.
A. There's the 3 pieces of information that I'm going to use. The A, the 8, and the 37. What we have to do now is, from the perspective of the 37, label these 2 sides using opposite, adjacent, and hypotenuse. And once we know their names, that will tell us which one of these 3 to use. What's the name of the side that is labeled A? What would we call it? Yep.
Opposite.
This is opposite. What about the side we've labeled 8? Yep. Hypotenuse. So we need a trig function that's going to involve opposite. That's the side we want to know. And it has to also involve hypotenuse. That's the side we already know. Tim?
You'd want to use sine.
Sine. So it's always the sine of, remember that's not multiplication at all. It's just that's the argument. It's the number we're going to plug into the sine formula. So we're going to take the sine of, what's my angle I'm using? Mabel?
37
30. Yep. So we're going to take the sine of 37 degrees. And sine is equal to, what's the formula again? What over what? Yep. Opposite over hypotenuse. Okay. And how do we get A by itself? Nick?
Multiply both sides by 8.
Multiply both sides by 8. Times 8. Times 8. That's gone. And there's your answer. 8 sine 37 equals A. We have to type that in. First of all, make sure you are in degrees, which I am. 8 sine 37. And that comes out to 4.815. We'll say 815. 4.815. So try that on your calculator. If you're not getting 4.815, something's wrong. If you are, then you're doing it correctly. Perfect. Questions on A? All right, now B. Do I have enough information there to use Pythagorean Theorem? Okay, I do. Any thoughts about whether or not I should use Pythagorean Theorem? Michael?
No, because you're not supposed to use numbers that you found.
Yeah, we're not supposed to use numbers we found. And if we use 4.815 and it's wrong, then B is going to be wrong. So let's find B the same way we found A. We could double check it with Pythagorean Theorem if we want, but I wouldn't use Pythagorean Theorem. Okay, now let's focus on a different color. Focus on what we're circling in red. Those are the two things that we're given. That's what I want to find. What's the name of side B? Sophie?
Adjacent.
That's adjacent. Alright, so this was to find A, and now this is to find B. Let's see, what trig function should I use that would involve adjacent? That's what I want to know. And hypotenuse, that's what I already know. Yep.
Cosine.
Cosine. So cosine of, what's my angle that I'm using? 37 degrees. So it's always cosine of an angle equals adjacent over hypotenuse. B over 8. All right, now, how would I get B by itself? Yep.
Multiply by 8.
Yeah, it's the same thing this time. Whenever the variable is in the top, you just have to multiply both sides by the number in the bottom. So the answer is 8 cosine 37. Just as a quick kind of mental check here, should B come out bigger than A, or should it come out smaller? What do you think?
Bigger.
Yep, it will be bigger. The biggest side is always across from the biggest angle. The smallest side is always with the smallest angle. And the one in the middle is the middle side. Also, any two sides added together cannot be bigger than the third. So that kind of limits us as well. For example, this couldn't come out any bigger than, like if it was 10, that's too big. Because 10 plus 4, no, that is what you want. Sorry, any two sides added together have to be bigger than the third. So like if B came out to 1, that's too small. Because 4 plus 1 doesn't give me a number bigger than 8. All right, so any two sides added together have to be bigger than the third. So in this case, B has to be at least, well, if it was 3, that's too small. So it's got to be about 3.2 at a minimum. So that when I add it to A, I get at least 8. Right? So it can't be smaller than 3.2, but we also know that it has to be the middle size, so it's got to be in between 4 and 8. So that narrows it down a little bit more. All right, let's type it in and see what we get. I like to do that just to make sure when I get my answer, I can quickly see if it makes sense. 6.389, and yeah, that makes sense. It's in between the other two sides, and that's what we thought. Any question on that type of problem? So that's solving a right triangle where you're given a side and an angle. I have one more with a side and an angle. Let's do part of it because I want to at least do something where the variable ends up in the bottom instead of in the top. And let's see if this one will work out that way. We're given alpha and A. Yeah, I think it will. All right, so let's try it. Set up our diagram. So let's call this A, B, C. That's alpha, and that's beta. So A, I can actually erase it and fill in the number. Well, you can keep the A there if you want. So A is 12.3. Alpha is 20. And we don't know anything else. So I'll usually just make a table. beta. This time they were a little bit more specific about what was what. In this diagram, they really didn't. They just said one of the angles is 37. We didn't know if it was alpha or beta, so we could choose. In this problem, you can't. They're telling you alpha is 20, make alpha 20. Okay. Beta, we don't know. And that's going to be the symbol when we don't know the right angle. So it's just kind of a habit that I write that. But we do know it's a right angle, so we don't need a special name. That was the Greek letter gamma, by the way. All right, so we got that, and we got A is 12.3. Okay, so anything I can find pretty quick first. Yep.
Beta.
Beta, what is it?
7.
7. Should we use beta to find B or C? Even though we know it's right? Yeah, you might think it's right, and you never know. You're taking a test, you think it's right, and it's not. Just don't use it. Go back to the 2 pieces of information that were given. Now, I want to solve for something where A ends up in the bottom. So, A is going to be, let's name that side. What's A? Yep, that's opposite. And let's see, we don't know B or C. What's B? Yeah? Adjacent. And what's C? Hypotenuse. So I just want to solve for something where B or C ends up in the bottom. Well, that's pretty simple. Let's just do, let's solve for C. What trig function would I use to solve for C? Caleb?
Sine.
Sine, right? The sine is opposite over hypotenuse. Madison, what's my angle? 20. How about Lindsay? What's my opposite?
12.3.
And my hypotenuse, Annalise?
C.
C. Okay. So, I'm just going to put something around that so we remember this is what we started with. Okay, what's in the blue thing? All right, so that's what we started with. What do you think I could do first on both sides here? Yep.
We should divide by 12.3.
I could, but then that would leave me with this on the other side. If I divide both sides by 12.3. We cancel out the 12.3 and leave me with a C in the denominator. Which then I could flip both sides. But let's do it a different way. Maybe just getting rid of the C in the denominator first. Yep.
Multiply each side by C.
All right, let's multiply both sides by C. And that's going to give me C times the sine of 20 equals 12.3. So all that it does is move the C to the other side. And now, what would be my last step to get C by itself? Sophie?
Divide by sine.
Divide by sine 20. So that's gone. And we get C equals 12.3 over the sine of 20. So now, look at what's in that box and compare it to what we started with. Can anybody just summarize what happened to get from here directly to there? Yeah.
You swap C with sine 20.
Yeah, all we have to do is swap the C with the sine 20. And that's how we're going to solve problems like that in the future. Okay. You can always do this out every time, but what's going to happen is when the variable's in the bottom, you can swap what's in the bottom with what's on the other side. All right. So, if you had x, or let's say 5 equals, let's say 3 over x, and you're trying to solve for x, all you have to do is swap the 5 and the x. And you're done. All right, so now let's take that in. So we've got 12.3 divided by sine 20. That gives me 35.963. All right, that seems reasonable. Because, I mean, the smallest side in this problem is 12.3. This angle is a lot bigger than 20, so this side should be a lot bigger as well. Okay. Any questions on how you would finish that up? Okay, I just wanted to make sure I showed you at least one where the variable ended up in the bottom, and then I gave you a couple where the variable was in the top. All right, let's look at the case where we're given two sides. Okay, this case is a little different. They also don't tell us which side is which, so we get to choose. All right, what do you think? First thing I should do here is. Yeah, maybe.
Draw a triangle.
Yeah, let's draw the triangle and label everything we can. So we got our angle. For now, I'll just label A, B, and C. Alpha, beta, I always start with that, and then I fill in what they give me. So I don't know which side is which, so it doesn't matter. Let's call A the 12.7, and let's call B, oh wait a minute, can I do that? No, they tell me the hypotenuse and one leg. So I can't choose which side is the hypotenuse. The hypotenuse is the 12.7. Even if they didn't tell me which side is which, if they've given me a hypotenuse and a leg, then the bigger number has to be the hypotenuse. Okay? So the hypotenuse has to be the 12.7. The 6.1, I can put that wherever I want. Let's call that A. Any questions why I labeled it the way I did? Okay, so let's make a table. And fill in what we know. So we've got this. We've got this. Again, I keep doing that. This is the right angle. And I put boxes around the three things I need to find. B, alpha, and beta. All right. What do you think I can do in this problem that I couldn't do in the last two? But this time I'm okay with it. Yeah?
You can find B.
I can find B. How?
Pythagorean theorem.
Why? I thought we didn't want to use Pythagorean theorem.
But you're getting two pieces, so you use it.
Yeah, it's not that we don't want to use Pythagorean theorem. We don't want to use things that weren't given to us. Well, everything here is given. So we can solve for B because everything's given. So A squared plus B squared, which we don't know, equals C squared. All right, let's do that out. 6.1 squared is going to give me 37.21 plus B squared equals 12.7 squared, 161.29. Okay, what do I do next? Tim?
Subtract 37.21 from both sides and then take the square root of both sides.
Yeah, so I'm going to do that in the same step. So I've got 161.29. I'm going to minus this 37.21. And we had B squared, so we're going to take the square root. All right, so square root of 161.29 minus 37.21. And that's 11.14. Okay, so I practiced rounding to 3 decimal places. Now I'm just going to practice rounding to 2. I just want to kind of show you a little of everything. The directions on the test will tell you how many decimals to use. But you've seen both. 11.14. Okay. Now, we can choose what side we want to find. What angle we want to find. So, let's find, let's see. Let's find alpha. Okay, just because it's alphabetical, it's first. But let's do that one. That was given, and that was given, and that's what I want to find. So everything is from the perspective of alpha for now. What is the name of the 6.1? Madison? Opposite. What about the name of the 12.7? Yep. Hypotenuse. And what trig function involves opposite and hypotenuse? Caleb?
Sine.
Sine. So let's set this up. So we're finding alpha. So the sine of alpha equals opposite over hypotenuse. What's different about this compared to any other problem we've done so far? Tim?
Where are we gonna divide it?
What would you divide by?
Divide each side by sine.
Sine of, divide each side by sine of what?
Sine of alpha.
You could, but then that would leave you with 1 equals 6.1 over 12.7 times sine alpha.
So that makes no sense.
Yeah, if you divide each side by sine alpha, it just moves it to the bottom of the other side. It's better where it is right now. So what else is different about this? We haven't seen one like this because what's different? Nick?
There's no variable. Or
There's no variable?
it's on the other side of the equal sign.
So there is a variable, right?
Yeah.
Yeah, there is a variable, but where is it? Yeah.
It's the argument.
It's the argument to the trig function. All right? That's like having a variable under a square root. You can do all the adding, subtracting, multiplying, and dividing that you want, and it's never going to get x by itself. When you have a variable inside of another function, like inside a square root function, the only way to get the variable by itself is to get rid of the function that is surrounding it. And for that, you have to use the opposite of the function. So in this case, if you had a variable inside a square root function, you would use the square function. Well, let's take a look at this a little bit more. So we have sine of alpha equals 6.1 over 12.7. We need to cancel out, again, I did this a little differently before, but the way we did it is fine. We need to cancel out sine. Just like you'd need to cancel out a square root. The way we cancel out sine is to use inverse trig. Inverse trig is the opposite, or it's the inverse of regular trig. And the way inverse trig works as an operation, you have to do it on both sides. So, if you had something like this, I would say, if I was explaining how to do that, I would say square both sides. That's how you get rid of that square root. You square both sides. The whole side. So even if you had something like this, and we've talked about solving problems like that, it comes out as a quadratic. We solved radicals. We had to square both sides. All of that and all of that, which now means we have to FOIL all that right-hand side out and solve it as a quadratic. Well, same idea here. We're going to take the inverse sine of both sides. There's two different ways you can write the name of an inverse trig function. This is generally how I do it, and what you'll probably see on a calculator. Some older books, you might see the words arcsine, arccosine, or arctangent. It means exactly the same thing. And all of these functions take an argument. Just like this, you can't just write this and ask somebody, what's the answer to that? Well, what's your argument? What are you taking the square root of? Right? I can't write this and say, what's the answer? Well, what are you plugging into it? I need to know the number that you're taking the inverse sine of. Or what's the thing you're taking the inverse sine of? Right? So now we're going to try that on our problem. Yep.
Is this just the same as 1 over sine?
No. So it's a little confusing because usually when you put a number up higher, it does mean that that number is an exponent. And usually that's true. And if you were to write something like this, that does mean this. Sine squared does mean sine squared, like that. When you put a -1 here, this is kind of a special case. This absolutely does not mean this. It is not raising sine to the -1 power. If you put any other number there, yes it is. 2 or 3 or 4, yep. But when you put a -1, that -1 is just a special symbol that means inverse sine. It has nothing to do at all with raising something to a -1 power, which would normally mean flip it. A little confusing, but you just have to remember that. It has nothing at all to do with a -1 power. I think that's why sometimes people write it like this, and that eliminates that confusion. Okay. So again, just think of that as a special symbol that means inverse trig, which is a totally separate button on the calculator. Yep.
Let's say we have sine squared and we need to get rid of sine squared. What would we do?
So if you had a problem like sine squared x equals 1/2, you can take the square root of both sides. And you would get sine x equals positive or negative 1/4. That's fine. Yep, that works perfectly fine. Because you can think of this as that. Doesn't matter what you have inside parentheses. If you want to undo squaring, you take the square root. You can put anything you want inside those parentheses. Okay, so, a good question. So we're going to use inverse trig on this problem. So let's go back to it. And we're going to take, that's the correct word, there is no multiplication at all here. We're going to use the inverse sine function, and we're going to plug all of that stuff into it. And I need to squeeze that in on the right, so I'm just going to move this over a little. You can use brackets, you can use parentheses, whatever, it doesn't matter. But I'm plugging everything on the left into the inverse sine function, and I'm plugging everything on the right into the inverse sine function. I did the brackets because I want to really emphasize there is no multiplication. Sometimes people see parentheses and they think, oh, multiplication. No, no multiplication. Just like square and square root cancel each other out, so do inverse sine and regular sine. So, the answer is the inverse sine of 6.1 over 12.7. So, inverse sine of 6.1 divided by 12.7. So, inverse sine 6.1, 12.7. Okay, that gives me 28.71 degrees. Okay, the answer here is an angle. That's what inverse trig always is used for. Inverse trig calculates an angle. 28.71. Now, if I was running out of time on the test and I had no other choice and I had to get it done, I would just subtract that from 90 real quick, pray I got alpha right, and go from there. But we can find beta the same way we found alpha. You don't need alpha to find beta. So, let's focus on what was given. And now, notice I circled a different angle. When you're doing inverse trig, you have to switch your perspective, because now you're choosing a different angle. So what does that mean? Those names don't apply anymore. You're standing in a different spot. So now, let's double check. Maybe one of the names still applies, but let's just double check them both. What is side A now? Yep.
Adjacent.
That's adjacent. Was there any change to side C? No. So I guess I could have kept that. All right. C is always the hypotenuse. What trig function involves adjacent and hypotenuse? Cosine. You might think, well, wait a minute. We just did inverse trig and we used inverse sine. Now we're using a different one. That's fine. Sometimes you use the same one. Sometimes you use a different one. All right? Adjacent over hypotenuse is inverse cosine. So cosine of beta equals 6.1 over 12.7. And what do I do on both sides to get beta by itself? Yep.
Take the inverse trig, so like the cosine. and
Yep.
one.
Take the inverse cosine of everything on the left. Take the inverse cosine of everything on the right. There's no multiplication happening in that whole problem. These cancel out. Technically, this is now approximate because we're going to round it. Inverse cosine 6.1 divided by 12.7. 61.30. And if we scroll back up, and you add those angles together, that's going to come out pretty close to 90. A little off because of rounding. Maybe it should have been 0.29, but that's the way my number came out. So, okay, any questions on that one? So those are the two different cases. Solve when you're given an angle on the side, solve with two sides. The two-side case is always going to require you to use inverse trig. You'll never have to use inverse trig if you're given an angle to start. That's all inverse trig does, is it calculates an angle. Does anybody feel like they need another one with the two sides? Would you use inverse trig here or no?
Yes.
Yes, you'd have to. You'd use Pythagorean Theorem if you want right away, get A, and then use B and C to find the two angles. Maybe you want to find the angles first, so you're not tempted to use side A. Right? Because side A is going to be something you find, so don't use it to find anything else. All right, so let's take no, I'm not hold off on that. No, actually, I probably should do it. All right, let's take a quick look at that. So we've talked about unit circle trig, where the sine was y, cosine was x, and tangent was y over x. Well, those formulas were very specific to a unit circle. That means the radius is how big on a unit circle? 1. Well, let's think about what would happen here if this wasn't a point on the unit circle, but let's pretend you had a point on a bigger circle. All right, so this just represents having a bigger triangle. That's all. So think of this point as having coordinates x, y. This side is x. This side is y. And the way you can figure out what's going to end up happening here is think about what we just learned. The opposite, adjacent, and hypotenuse. And that's going to give you the formula you need, pretty much. So the sine originally would have been what letter on the unit circle? What letter was sine equal? This was from a couple weeks ago, yeah?
Y.
Sine was equal to y. Let's look at sine, what sine would equal now on a bigger circle. So instead of having a coordinate on a unit circle, I've got a coordinate on a bigger circle. Well, what did we just learn sine is? It's the what over the what? Yeah?
Opposite over hypotenuse.
It's the opposite over the hypotenuse. Theta, I didn't have enough room to put it, so I just put an arrow. Theta is right here. What side is opposite theta in the big triangle? So it still has a y in it, but this is the difference. What's the hypotenuse?
R.
Yeah, hypotenuse is r. Let's look at the cosine. Cosine is adjacent over hypotenuse. What side is adjacent to theta? Yep, x. And the hypotenuse is r. Tangent. Anyone have a guess what the tangent's going to be? It's actually the same thing that it was on the unit circle. Michael?
Y over X.
Y over x. Now, look at what happens if you let r be what it is on the unit circle. What is r again on a unit circle? It's 1. If you fill in 1 for r, look what you get. Y over 1. That's the original formula I taught you. I said sine is equal to y. It was really y over 1. I didn't have to tell you it was over 1 because it didn't make a difference. Cosine, I said cosine equals x. What I really could have said is cosine is x over 1. But again, dividing by 1 didn't matter. Now it does matter because r isn't 1. What about your cosecant? What do you think that'll be? Yep,
R over Y.
r over y. Your secant? Yep,
R over X.
r over x. And what about your cotangent? Yeah,
X over Y.
x over y. So if you have a random coordinate that's not on the unit circle, these are the 6 formulas that you use. If you change all the r's to 1s, you'll get all the original formulas I gave you. 1 over y, 1 over x. And that's what I taught you originally when we did unit circle. So there is an extra thing you have to figure out here. You'll be given a coordinate. It'll have an x, it'll have a y. But the extra thing you need to find is r. How can you find r if you're given the x and the y? Yeah.
Pythagorean theorem?
Yeah, that's the only extra step. You have to use the Pythagorean theorem to find the r, and then you can fill them into those formulas. So, you don't have to write these down, but these were the original formulas. That we learned when we did unit circle trig. And now, I just extended all the formulas for you right there. So these are the general formulas to do trig on a circle of radius r. So I wrote it down again here. So sine, cosine, tangent. Cosecant, secant, and cotangent. Same thing I just wrote on the other page. That's what they are. Trig functions in terms of a circle of radius r. All right, so it says find the 6 trig values of the coordinate 2, 3. So if you're not sure if 2, 3 is on the unit circle, and you're like, well, wait, should I use the formulas he taught us on originally, or should I use the new ones? Well, use a piece of graph paper, which I I have in here, and you could use on a test. Let's put in this, and let's put the point 2, 3, because it said that point is on the terminal side of an angle. Here's your initial. Here's your terminal. And let's see if we make a circle, if that's the unit circle. Does that circle have a radius of 1? No. Point 2, 3 does not have a radius of 1. We are going to have to figure out what that radius is by making a triangle. This side is 2, and this side is 3. So what would be my radius in that case? Yep.
Square root 13.
If you use Pythagorean Theorem, you will get square root of 13. And really, this is the same problem you had in last night's homework. Just tell me the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent. All right, so we'll do the first 3. Sine is y divided by r. Well, this is your y. This is your r. We just used to call it hypotenuse. Now I'm looking at it as a radius of a circle. Same thing. What's the sine going to be in this case? Tim?
3 over square root 13.
Yeah. So 3 square root 13 over 13. And see if you can get the cosine and the... what about my cosine? What would that be? Okay, that's x over r. Sophie?
2 over square root 13.
And when you fix it?
2 square root 13.
Perfect. And what about my tangent? What's my tangent? Madison?
3 over 2.
Take a look. Tangent is defined to be the y value over the x value, which in this case is 3 over 2. If you remember it as opposite over adjacent, it's the same thing. Just a different way to think about it. And then what would you do with these 3 to get the other 3? Yep.
Find the reciprocal.
Yep, find the reciprocal. So any questions on how you would find the cosecant, the secant, or the cotangent? All right, so it's just a little different way of wording the question, but the steps behind it is exactly the same. We got that. All right, let's solve for the angle in example 3. I'm going to go back and do it on the same page. I'm not going to do it here because I already have the sketch. What's one of the simplest trig functions that we use? And it's one of the ones we have a button for, but it's one of the ones that's used most often. Yeah. Sine. The very first one that we always do anytime we're doing a problem, we always do the sine out of the 6. We do it first. So let's find this angle using the sine. You could use the cosine, you could use the tangent. You could use any of them. But sine is usually the easiest one. So I wanted to set up an equation involving sine. And this is now example 4. What would the sine equal? We already had it, yeah.
3 times the square root of 13 over 13.
Yeah, it's just 3 times the square root of 13 over 13. I'm just going to write it down here so I have a little more space. 3 root 13 over 13. And what could I do to get theta by itself? Yeah.
Take the inverse.
Yeah, take the inverse sine. That cancels. Take the inverse sine. And now, let's see. Inverse sine of 3 square root 13. Get out of the root, divided by 13. So that angle is 56.31. 56.31. And that was degrees. Any question on that? Okay. Now, 2, 3, that point is in the first quadrant. So any angle, think about in the first quadrant, is acute. Because this is 0, 90, 180, 270. Just like if I said to you, any coordinate with a negative x and a positive y, well, that would be between 90 and 180. If you had a coordinate with a negative x and a negative y, that would be between 180 and 270. Just looking at the quadrant the coordinate lands in. So, what would happen if we had to do a problem like this? 2, negative 3. Well, we have to take into account that that y value is negative. We can still do inverse trig, but this is what we want to do. We want to first find what is called the reference angle. And I'll show you how you do that. There's a different formula for each quadrant. But the reference angle is basically the absolute value of the inverse sine. Okay, that's called your reference angle. Basically measures the distance that your angle is from the x-axis. So if you had quadrants, if you had an angle here, well, in quadrant 1, your angle is the reference angle. A reference angle is always between 0 and 90. And in quadrant 1, it's automatically between 0 and 90. In quadrant 2, that would be your reference angle. The goal would be to find this. That's the angle. This part is called your reference angle. What do you think you would do with your reference angle to find an angle like that? You're going to know this. You're going to want to find that. Yep?
Subtract it from 180.
Exactly. You're going to subtract your reference angle from 180 if you're in quadrant 2. In quadrant 3, you could have a triangle like that. That's your reference angle. You're going to want to find that. So what do you think you would do in quadrant 3 with your reference angle to find that part in green? Yep.
Subtract it from 270.
No, we don't want to subtract it from 270, especially think about if your angle was more like this. It might not split right in the middle. If it did, it wouldn't make a difference. But if you subtract from 270, like let's say that was a 5-degree angle right here. If you subtract it from 270, that would put you just a little bit like that. Yep.
You add it to 180.
Yeah, we're going to add it to 180. And then in quadrant 4, that would be your reference angle. So how would you find this in quadrant 4 if you know that is your reference angle? Tim?
Now do you subtract from 270?
No, because that would put you back this way.
Oh yeah, so you'd add 2, yeah, I don't know.
Like let's say that this was 10. How far around would you have gone? Think of it that way. Yeah?
So you subtract 360.
You'd subtract it from 360, because if this reference angle was 10, that means you're 10 degrees shy of going all the way around, so you went around 350. That's the formulas I'm going to write down right now. So once you have your reference angle, by taking the absolute value of the inverse sine, if you're trying to find an angle in quadrant 2, you do 180 minus your reference angle. If you're trying to find a formula in quadrant 3, it's 180 plus your reference angle. And if you're trying to find a formula in quadrant 4, it's 360 minus. If you're doing this in radians, substitute what I just wrote down in blue. This is how you find the reference angle. It's the absolute value of the inverse sine. Okay. Any question on those formulas? Okay, so we'll try an example. It says, given the point 2, -3 is on the terminal side, find theta. All right. First of all, what quadrant am I going to be in? Yep.
Second.
Let's see. Second quadrant would have to have a negative x value. So we're definitely going right, and then 4. We're going right and down. So we're going to be somewhere 2 to the right, 3 down, maybe like that. So my goal is to find this. What I'm going to find first is that. That's my reference angle. So let's make a triangle. This side is, let's see, that's my 3, that's my 2. What's my hypotenuse? Yep. It's the same triangle we had before, it's just rotated into a different quadrant. It's the 2, 3 triangle. Okay. So it's still square root of 13. Okay, so square root of 13. So remember, you could, and I'm going to jump right to the inverse trig. You could write sine theta equals 3 over square root of 13. Opposite over hypotenuse. But we can just jump right to the final answer. Inverse sine of 3 over square root 13. Now you might say, well, wait a minute, you just left square root in the bottom. I don't really care. That's not my final answer. I'm going to type that in and get a decimal. If you want to type in a square root in the bottom, that's fine. You can leave it like that. I know we fixed it before, but let me show you what happens if you type it in. We already know the reference angle. We just did this in the exact line above on the calculator. It's 56.31. That's my reference angle. What do I do with that reference angle to find the big angle? Yep.
From 360.
Subtract it from 360. So 360 minus my reference angle gives me 303.69. So I'm just going to put that as my answer. I'll just call it something different. I'll call my reference angle theta 1, and then I'll call the actual answer to the problem theta. So actually, what did I get again? 303.69. Now, this inverse trig works fine as long as you don't have a point on an axis. Because if, let's say you had a point here, what's the x value of that point? It's 0. So when you have a 0, and there are formulas we talked about today that have x in the bottom, so you could end up with a 0 in the bottom, you can't really use inverse trig. You just have to remember that if you're on an axis, your angle is either 0, 90, 180, or 270. You have to remember that. But any other point other than having a 0 in it, you can do the inverse trig that I showed. And we've done this before. Trig functions of quadrantal angles come out to 1, -1, 0, or undefined. Okay. Any questions on that? And the last thing, we're gonna save, you don't need it for tomorrow. So it's simple, but I'll teach you this some other time. The ASTC. All right, so that's the homework for tonight on 361. Tomorrow we will have our test. If you have any questions on the homework, feel free to stop by any period. One we already have, 4 or 9. Okay, so next period or last period, I will be available, as far as I know right now, to answer any questions.